The spring of 2019. Lancaster County, Pennsylvania. A retired electrician named Carl Brennan is standing in a field at dusk, and he is looking at 14 wind turbines. 12 of them are dead, frozen at the bearings, blades split, generators seized into solid rust. The kind of dead where you can feel the money those machines cost and know it is gone forever. One is still spinning, quiet, smooth, feeding a clean current down a copper line into a white farmhouse where a porch light burns warm against the coming dark. Carl stood there for a long time. He is an electrician. He has worked with wind systems for 20 years. He has seen more failed turbines than he can count. But he had never seen one like this. Not still running. Not like this. He walked up to the farmhouse and knocked on the door. The man who answered was Amish. His name was Eli Stoltz. He had built that turbine himself, with hand tools, from a description in a government agricultural pamphlet printed in 1938. It had been running for 11 years without a single repair. The total cost of parts, including the tower, was under $120. Carl asked him how. Eli looked at him like the question was strange. He said, "The design is correct. When the design is correct, it works." I want to tell you what Carl learned that night. And I want to tell you what Eli understood about wind that 90% of American homeowners do not. Because what he understood is the same thing the residential wind industry has spent the last 2 decades hoping you never figure out. If you did, their entire product line, every $1,400 Amazon turbine, every $6,000 Primus Air, every glossy brochure promising free energy from the sky, would collapse overnight. This is the story of why nearly every backyard wind turbine in America dies within 12 months. Why one specific design from the 1930s survives for decades on almost nothing. And why the Department of Energy quietly stopped funding small wind research in 1996, right as the technology was about to become unkillable. Start with the numbers, because the numbers are what make this story real. In 2014, a research group called the Cadmus Group ran a field study for the Department of Energy. They tracked 161 small wind turbines installed on residential properties across Massachusetts, New York, and Wisconsin. Real homes, real conditions, real weather. Within the first year of operation, 64% of those turbines were either non-functional, producing less than 10% of their rated output, or had been physically removed by the homeowner. By year 3, that number climbed above 88%. The report was titled Massachusetts Small Wind Initiative Final Evaluation. It was published quietly, posted to a government server, and never made it into a single mainstream news cycle. Page 47. That is where the conclusion lives, buried in the middle of a document that nobody reads. The conclusion says, and I am paraphrasing only slightly, that the small wind industry as currently constituted does not deliver reliable energy to residential customers under typical siting conditions. Translation: the turbines do not work. Not the cheap ones from China. Not the mid-range ones from the established manufacturers. Not even the premium models with the lifetime warranties that quietly require the company to still exist when you try to file a claim. And here is the part that should genuinely make you angry. The industry has known this since at least 2008. There is a man named Mick Sagrillo. He is a small wind consultant out of Wisconsin who has been shouting about this for almost 20 years, in forums, in trade publications, in testimony to state energy boards. His phrase, from a 2011 Home Power magazine interview, was that 90% of residential wind installations are a monument to the homeowner's optimism and the installer's commission. Nobody listened. The subsidies kept flowing. The turbines kept failing. And the design that actually worked, the one Eli Stoltz has bolted to a 40-foot lattice tower behind his barn, was discontinued from commercial production in 1957. To understand why the right design disappeared, you have to go back to before the Second World War. Because what existed then was genuinely remarkable, and what happened to it was not an accident. Before the grid reached America's farmland, small wind was a serious industry. Not a hobby, not a fringe experiment. A real, mature, commercially developed technology that powered thousands of rural homes across the Great Plains. The flagship company was Jacobs Wind Electric. Founded in Minneapolis in 1925 by a man named Marcellus Jacobs, who grew up on a Montana ranch without electricity and built his first wine machine at 19 because he needed one. The machines Jacobs built were extraordinary pieces of engineering. 3-blade direct drive turbines with a flyball governor, a brushless alternator design, and a tower so overbuilt it could survive the ice storms that roll across the Dakotas in February and snap a modern fiberglass blade like a twig. These units did not just survive. They ran. Plains farmers reported 30, 40, sometimes 50 years of continuous operation with no major service. The bearing loads were low. The governor kept the rotor from overspeeding. The components were steel and copper and cast iron, built to the tolerances of a world where you could not order a replacement part from a warehouse in Memphis and have it in 2 days. You had to build it to last. Jacobs Wind Electric was not the only company. There was also Wind Charger, out of Sioux City, Iowa, and a dozen smaller regional manufacturers who understood that a farm machine had to work without a service contract. Franklin Roosevelt signed the Rural Electrification Act, designed to extend grid power to the 30% of American farms that still had none. It was a genuine public good. The grid was real and it was transformative, and within 15 years, it had reached most of the country. But what it also did, quietly and completely, was kill the small wind industry. Why build a turbine when you could simply connect to the line? The market vanished almost overnight. Jacobs shut down residential production in 1956. Wind Charger followed shortly after. The designs were not destroyed. They were simply no longer made. And the institutional knowledge of how to build them, how to balance the blades by ear, how to set the furling angle by feel, how to wind your own field coils by hand, evaporated into a generation of old men in flannel shirts who still remembered. Most of those men are dead now. Most of them. Not all. The Amish, because they never connected to the grid in the first place, never stopped using these machines. They kept rebuilding them. They kept teaching their sons. And while the rest of America was buying cheap turbines off the internet with 500-watt ratings that produced maybe 40 watts in real-world conditions, the old order communities of Ohio, Pennsylvania, and Indiana were quietly running farms on machines designed before penicillin was widely available. Eli Stoltz did not invent his turbine. He is the first to say so. He copied it, almost bolt for bolt, from a 1938 USDA publication called Farmer's Bulletin No. 1773. The title was Wind Electric Plants for Farm Use, and it was written by a USDA agricultural engineer named Henry Putnam. That bulletin was reprinted 4 times between 1938 and 1945. It was distributed to county agricultural extension offices across the country. Farmers used it. Then in 1947, as part of a broader USDA shift toward promoting rural grid connection, it was quietly pulled from active circulation. The document is 46 pages long. It contains complete schematics, materials lists, blade carving templates drawn to exact dimensions, tower construction details, and footing specifications, battery bank wiring diagrams for 12, 24, and 48-volt systems. Every single specification a homeowner would need to build a functioning wind plant from scratch, using materials available at a 1938 hardware store. No exotic components. No rare earth magnets. No circuit boards. Nothing that can demagnetize in a heat wave or short out in a salt air climate. I have a scanned copy on my desk as I am recording this. You can find it through the National Agricultural Library archives if you know to look for it. Most people do not know to look. That is the entire problem in one sentence. The knowledge was not destroyed. It was simply allowed to fall out of public consciousness, replaced by a marketing layer of high-tech looking products that, in the real laboratory of a real backyard with real wind, do not function. The bulletin survived because agricultural libraries do not throw things away. The knowledge survived because old order communities do not depend on the commercial market to tell them what works. Everyone else is buying turbines that fail. And a man named Eli Stoltz is sitting on his porch reading by the light of a machine that has been running since the Obama administration's first term. There are 3 specific differences between the 1938 design and what is sold today. 3 engineering choices that determine whether a turbine lasts 2 years or 40. They all sound boring, which is precisely why marketing departments do not put them on the brochure. The first is rotor size and blade count. Modern small turbines almost universally use 3 thin blades on a small rotor, usually under 5 feet in diameter. This looks sleek. It spins fast on the showroom floor. The marketing photos are dramatic, but the physics are brutal. A small, fast-spinning rotor places enormous cyclic stress on the bearings. Every rotation is a load cycle. A modern turbine bearing might see 40 million rotations in a year. The mechanical fatigue accumulates with every single one. The 1938 design uses a larger rotor, between 8 and 12 feet in diameter, with thicker blades that turn slowly. Slow enough that you can almost count the revolutions by eye in a moderate breeze. That same year of operation translates to 4 million rotations. A 10 times reduction in fatigue cycling, which translates, almost directly, to a 10 times increase in bearing life. There is no trick to this. There is no patent. It is just physics. Stress times cycles equals failure. Reduce the cycles, and the failure gets pushed decades into the future. The second difference is the generator. Modern turbines use permanent magnet alternators with rare earth neodymium magnets. These magnets are genuinely powerful. On paper, they produce excellent power density for their size. In practice, they have 3 serious weaknesses that the spec sheet does not mention. They are brittle. Drop a strong neodymium magnet on a concrete floor, and it can shatter. Inside a turbine that vibrates in gusty conditions for years, that brittleness becomes a liability. They are heat sensitive. Neodymium magnets begin to lose field strength at temperatures that a turbine can easily reach in summer sun. Partial demagnetization is permanent. The turbine loses capacity and never gets it back. And when the turbine overspeeds in a strong gust, which happens every time the electronic braking system lags even slightly behind the wind, the eddy current heating from extreme RPM can demagnetize the entire rotor in a single event. One bad storm. Everything gone. The old design uses a wound field alternator. In some versions, it uses a modified automotive alternator rewound for low RPM output. These are not as efficient at peak. If you put them side by side in ideal conditions, the modern machine wins on pure output per pound of generator. But across a 40-year operating window, in real weather, in real humidity, in real temperature swings, the wound field design is vastly more durable. There is nothing to demagnetize. There is nothing brittle to fracture. There are field windings that can be re-wound if they ever fail, using copper wire available at any electrical supply house in any town in the country. Eli Stoltz could repair his generator with tools he owns and materials available in his community. The owner of a modern turbine with a failed permanent magnet alternator has to ship it to a specialty repair shop, if one even exists for their model, and pay a rebuild cost that often exceeds the original price of the turbine. The third difference is the one that almost nobody talks about, and it is arguably the most important. The furling mechanism. A modern turbine relies on electronic braking or electronic pitch control to protect itself in high winds. When the wind exceeds rated speed, a control board sends a signal, a brake activates, pitch changes. The rotor slows. The turbine survives the gust. That is the theory. Here is what actually happens. Control boards fail. Sensors corrode. Brake pads wear. Pitch motors cease. In salt air near the coast, this process takes 18 months or less. In high humidity climates, not much longer. And when the electronics fail, the turbine has no protection whatsoever. The next gust above rated speed simply tears it apart. Blades separate. The rotor overspeeds past its structural limit. The whole machine destroys itself. Carl Brennan told me he has seen this happen 3 times in person. A wind event, a gust, and then nothing left on the tower but a bent shaft. The 1938 design has no electronics. None. Zero. It uses a purely mechanical side furling tail. A hinged plate mounted offset from the rotor axis. In normal wind, the geometry holds the rotor facing into the wind. As pressure increases beyond a calibrated threshold, the aerodynamic force on the tail overcomes the hinge resistance, and the tail swings the rotor sideways, angling it out of the wind. The rotor slows. The gust passes. The tail swings back. The rotor faces the wind again. No circuit board required. No sensor. No motor. No software update. The mechanism works the same way in 2025 as it did in 1938 because gravity and steel have not changed. Eli Stoltz's furling tail has functioned through 11 years of Pennsylvania weather, including the derecho of 2012 that hit the mid-Atlantic at 80 miles per hour and knocked out power to 4 million homes. His porch light stayed on. I want to show you the numbers now, because this is where the argument against the old design completely collapses. A $6,000 modern turbine with an 18-month average failure rate has an effective cost per year of operation of around $4,000, accounting for the replacement cost that most owners face at year 2. If it lasts 3 years, you are at $2,000 per year. If it lasts 5, which is above average based on the Cadmus study, you are at $1,200. Eli Stoltz spent $120 in parts. 11 years of operation. His cost per year of running electricity is $10.90. His output is not massive. The 1938 design in the Bulletin produces between 250 and 1,000 watts depending on rotor diameter and wind speed. For a farm or homestead running a 12-volt or 24-volt battery system, this is genuinely useful power. Lighting, phone charging, small appliances, refrigeration with the right setup. It is not grid replacement. Nobody is running a modern suburban house on a single machine with an 8-foot rotor. But that is not what these families are trying to do. They are trying to produce reliable, reparable, affordable electricity from the wind that blows across their land. And on that specific goal, the design from 1938 is not just competitive with modern turbines. It is not even a close comparison. It simply wins. Every time. In every measurement that matters outside of a laboratory. Carl Brennan spent 2 days at Eli Stoltz's farm that spring. He asked every question he could think of. He took photographs. He measured the rotor with a tape measure. He traced the furling tail geometry on paper. He watched the machine respond to a wind shift and understood, for the first time in 20 years of electrical work, what a self-regulating turbine actually looks like. He told me later that the experience was one of the stranger things to happen to him professionally. He had spent his career working with modern systems, sophisticated equipment, computer-controlled inverters, variable pitch blades, all of it designed to be maximally efficient. And here was a machine built from a pamphlet older than his parents, spinning quietly on a hand-built tower, doing something none of the sophisticated equipment could manage. It was just working. He asked Eli whether the machine had ever given him any trouble at all. Eli thought about it. He said the tail hinge had gotten stiff once, maybe 6 years back. He had taken it down, cleaned the hinge pin, oiled it, put it back up. A Saturday afternoon. That was the full maintenance history of 11 years. Carl did the math. He had spent more than that on a single service call for a modern turbine that still did not work correctly afterward. He drove home from Lancaster County and started looking for the Putnam Bulletin.